Okay, we are in a unit about sequences. I found my first of errors in my PowerPoint here, but what I'd like you to do is just write down the key information about sequences in your notes. So the essential question is, what are sequences and how they work? We're going to talk about what they are, what they look like. So sequences are functions. That means that they have a predictable outcome, and each input has exactly one output. So sequences are special functions, and what makes them special, and here's one of my typographical errors, is the sequences always start with the first term. So this one is the first term, and if we were to put it in a table with sequences, we use the input of n and an output of t of n. That tells you it's a special kind of function where the inputs are counting numbers, 1, 2, 3, 4, etc. And that means the domain, the input possibilities are always just 1 and the numbers greater than 1, and they're counting numbers. Taking this sequence and putting it into a table, the first term is 1, the second term is 1, the third term is 2, the fourth term is 3, and the fifth term is 5, and we can continue that process by adding the number before it. That's how we generate that sequence, which is what we're going to talk about. So a function is, and we've been dealing with functions all years, any situation where it's predictable, or you can predict what the output's going to be, and each x, or each input, has exactly one output. That means that if you put it into the rule, only one thing can come out of it. So sequences are special kinds of functions because they have a limited domain or limited inputs to the counting numbers. 1, 2, 3, 4, 5, 6, 7, and never fractions, whereas a function would allow you to possibly have an input of -1, or 1/2, or a counting number like 5. So I'm going to talk about a sequence that's related to a linear function with a rule of 2n, or 2x. So -1 times 2 is -2, 1/2 times 2 is 1, 5 times 2 is 10. This is the function of 2x. The sequence that would be similar to it is going to have 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and you'll notice that there's a sequence generator of 2 and a growth factor or slope of 2 in both situations, but the sequence key issue is that it has counting numbers at its input. So its domain, or its inputs, are restricted to n being bigger than 1 or equal to 1, and it's always counting numbers. Because of that, when we make a graph, by the way, for a function, the graph would be a line, straight line, but with sequences it's going to be discrete points at 1, 2, at 2, 4, at 3, 6. And I didn't have you do that when you made your graphs for your sequences, but we're going to be clear about that in the future. It was really bad. I'm going to go back and do that. You can classify sequences. There are linear sequences, exponential sequences, quadratic sequences, other ones we're not going to talk about, but we're going to focus mostly on arithmetic and geometric. A lot of you have already found some really clear patterns for quadratic, but we're going to focus mostly in this unit on linear and exponential because we're going to get to the place where we can write the rules, and writing quadratic rules are a little more challenging, and so we're going to push those a little farther into the year. So arithmetic sequences you have a lot of experience with. They are linear. They grow by adding the same number over and over again. the special difference is that inputs are always just going to be 1, 2, 3, 4, not fractions, not negatives. So the big difference is going to be that, for example, in this one, we have a sequence generator of -2. We could call it the slope, we could call it the growth factor, we could call it all the rate of change, just like we used with linear functions. But arithmetic sequences have that special factor of having only 1, 2, 3, 4, 5, 6 as its inputs or its domain. And because of that, the graph has these discrete points. They're not continuous. We're not connecting the points. But here we have a -2 for every one. And this other one over here has a growth factor or a slope or a sequence generator of 1.5, which you can see in a slope triangle right there. But because it is a sequence, we're only going to have these discrete points and not a continuous thing. Arithmetic, linear, whoops, and wonky. So geometric sequences are exponential. They grow by multiplying or dividing by the same number, and they create upward curves when the multiplier is greater than 1, and downward curves when the multiplier is in between 0 and 1. We looked at a couple different ones in our work together. This one has a multiplier of times 2, and you'll notice that it's an upward facing curve, and I'm going to follow the path of the curve with the red, but I notice I do not connect those points because we do not have inputs for 3.5 and 4 and 2 7s and whatever. So it's an upward facing curve. It's got a positive greater than 1 multiplier. And if you can describe the multiplier as a divider, I hope you can hear my dishwasher right now. A multiplier is a divider, so this one you can think about it as dividing by 2 or multiplying by 1/2. And because that's true, since it's a divider, or you're multiplying by a fractional number, a number between 0 and 1, then you're going to see this downward facing curve. So exponential curves are geometric. So that's how we classify exponential sequences. Sequences, they're going to end up giving you, the rule will be some sort of squaring. And but when we look at the sequence, when input is 1, 2, 3, 4, 5, we're going to begin to see that it grows by increasingly adding, but the number that you're adding is increasing by the same amount each time as well. And so you have experience with 2 of these from the work we did. The 8202818 one, it grows by -6 and then -2 and then 2 and then 6 and you'll notice that it's growing, the number you're adding each time is growing by 4. So this next time we would be doing 14 more. And so we would end up with 32. It's going to be part of a parabolic curve. If we continued, we'd create that parabola, but this part is not part of the sequence. And then if we look at the other one, which was 0, 4, 9, 16, 24, we can you can see that this is going to be the term number -1 squared. So this is term number 1, not term number -1. Yeah, squared. Term number 1 would be 1 minus 1 squared, which is 0. Term 2 would be 2 minus 1 squared, which is 1. Term number 3 would be 3 minus 1 squared, which is 4. It creates a part of a parabola. The rest of it would be back here if we were visualizing it, but it's not part of the sequence. And then just like the one before it, this one you can describe as growing by the odd numbers, but how much you're adding each time is growing by 2. So quadratic ones are parabolic. So the last sequence that we just looked at is the Fibonacci sequence. It's not arithmetic. It does not grow by adding the same number over and over again. It is not geometric or exponential, where it grows by multiplying or dividing by the same number over and over again. And it's not quadratic. There's not an increasingly a number that's added each time and increases by that number each time. The Fibonacci sequence is a special sequence that you get for the input or the term number. You get the next one by adding the one before it. So term 2 you get by adding, actually term 3 you get by adding term 2 and term 1. So 1 plus 0 is 1, and then term 4 is 1 plus 1 is 2, and term 5 is 2 plus 1 is 3, and it goes on from that. Even though it's a weird sequence, it's seen all over nature. It's seen in the shape of a nautilus shell, in the circular pattern of rose petals, in a lot of succulents. It's a very cool pattern. You can go back, you can look all over the internet for interesting things about it, but we will be focusing mostly on arithmetic, linear, geometric, which is exponential. Those are the main two focuses, and then some work also with quadratic. From after this, I would like you to go ahead and do the work in your packet on the tile patterns, which are like a visual sequence. You only have information about tile pattern 1, tile pattern 2, not tile pattern 2.5. So you're still going to be looking at discrete points when you make the graph, and you'll be looking to see, are they arithmetic, are they linear, are they geometric? I said that wrong. Are they arithmetic or linear? Are they exponential, which is geometric, or are they quadratic?